Good evening, everyone. Good to see all of you here, people who think that the future of our planet is more important than watching the Lakers play tonight. So we you forgot about that, right? Well, we're in for a very special treat. Henry Pollack has spoken here before, 2003. When he was here then, he had spoken about what was a new book then, Uncertain Science, Uncertain World, which is still a remarkable book. And he's now going to speak to us about his latest book, A World Without Ice. So let me tell you a little bit about Henry Pollack. He was born in Nebraska. His father was a farmer. He went to Cornell. He got his bachelor's degree in Cornell, went back to Nebraska, got his master's degree, and then got his PhD from the University of Michigan. He went from Michigan to do a postdoc at Harvard. He went back to the University of Michigan, and he's been at Michigan now for almost 50 years. He's a professor emeritus, a professor of geosciences, amazing guy. He was chair of the department, associate dean for research, and in addition to being a wonderful teacher and scholar, he has served in numerous important advisory capacities. He's been on NRC, National Research Council committees. He also has been a member of the IPCC, the Intergovernmental Panel on Climate Change, and so he was one of those people for whom the Nobel Peace Prize was given, and he shared in that prize. He also has been a leader in the Vice President Al Gore Climate Change Initiative. He has helped train the people to go out and make these presentations. And in June, later this month, he goes back to Nashville, and he will be the one who's giving the science overview to all of this group of new recruits to go out and save things. He's an elected fellow of the American Geophysical Union and the Geological Society of America and the American Association for the Advancement of Science. And we had a lot of fun with Henry this afternoon. He gave a wonderful informal talk to some of our educators. I want to read something from, it was a person whose name is Leah DeMuchel, and she wrote, "What would be nice is if a brilliant geophysicist, maybe one who'd spent decades traveling the world conducting scientific research, helped win a Nobel Prize for sounding the alarm on climate change, had the soul of a teacher, and hey, if we're dreaming, told fabulous stories, would write a book. Wouldn't we all be better off if there was in one good volume marvelously credentialed science, covering the entire known history of world climate with serious smarts and peppered with entertaining anecdotes? I'm not kidding about this. We don't get past page 3 in this book before we pay an accidental visit to a nude beach, and maybe organizing the whole issue in such a way to take the overheated politics out of the debate." Henry Pollack wrote such a book, and he's going to talk to us this evening about that wonderful book. Please welcome Henry Pollack.
Thank you. Hello, everyone. It's nice to be back at the Aquarium of the Pacific. As Jerry mentioned, I was here in 2003, and I realize now that the ticket is that you have to write a book to get a dinner and a talk here at the aquarium. But it's a wonderful place. I enjoyed my first visit very much, and I came back today and spent a little time wandering around the exhibits. And what an exciting place it is. There are a zillion kids running around, and not just running around, but they have their nose up against the aquarium tanks and observing all the great things that are happening and listening carefully to the docents. So it's quite a treasure that you have here. As Jerry mentioned, I want to talk about my new book, and it's called A World Without Ice. And the reason I've chosen to talk about climate change through the Prism of Ice is that ice plays a very big role in the global climate system, and it's a very sensitive indicator of changes in the climate system. And so by focusing on ice, you are looking at a monitor of climate change that is telling an alarming story. But ice has been a part of the Earth's climate for a long, long time, and in framing the book, start the story about 20,000 years ago at the peak of the last ice age. It's amazing that only 20,000 years ago, a good part of the northern hemisphere was covered with ice, and very few people living on the planet at that time. Perhaps only a million people were walking the face of the earth. When you think of that today, that's about the size of the city of Detroit, or maybe Long Beach even, for that matter. How big is Long Beach? 500. So half of the people were from Long Beach. But at any rate, you get the picture that there's an awful lot of ice and very few people. And as we let the story of climate change march on, we reach a very gradual tipping point where there are a lot more people and a lot less ice. And if we carry it on even further, there's the trends that we are observing today, if unabated, unmitigated, could lead to a world without any ice. So I want to take you on that journey from a time when there was lots of ice and very few people, and carry it forward to the present day where there's lots of people and very little ice, and then have a look at what might be in store for the future. So let us begin. I don't think I need this. That's just an appliance sitting up here now. I actually have a mic right there. We're going to begin at the peak of the last ice age. And here's a map of North America showing the extent of the ice cover, nearly all of Canada extending into the northern part of the USA, and in the high mountains of the Rockies and the Sierra, there were thick sheets of mountain ice. And it's kind of hard to envision what a place covered with ice really looks like. And today, if you wanted to have such a vision, you would go to Antarctica. And this is a satellite mosaic of Antarctica, and it is basically a continent covered with ice. There are a few rocks poking out along the shoreline. There's a mountain range that cuts across the Antarctic from about here, coming across like that, and there's some rock that's exposed along that mountain range. That's called the Transantarctic Mountain Range. But basically, it is a big blanket of ice over the entire Antarctic continent. And if you get a close-up look at it, this is an aerial view above the South Pole Station. These buildings are where the research station, the Scott Amundsen Station, are. And this long strip here is a landing strip where supplies are brought in by aircraft. But you can see in the background that it is really just a vast, unbroken expanse of ice. And that's what North America and Northern Europe looked like only 20,000 years ago. This ice pile spills off towards the sea in all directions, and it flows from the polar plateau down giant valley rivers of ice that we call glaciers, and this ice creeps down towards the sea. It moves on the order of maybe 100 meters a year. It's not very fast. That's about the length of a football field. And so at New Year's Day, if the ice started at one goal line, a year later it would be at the other goal line. You all have heard the term, someone moves at a glacial pace. Well, that gives you a feeling for what a glacial pace is. So this ice comes down these valleys, and ice is a prodigious eroder of rock. It can move rock like a bulldozer and carve great valleys as it moves. And once the ice disappears, you can see the landscape that ice has produced. One familiar to you in California, you don't even have to be a Californian to appreciate this one, is Yosemite Valley. And it's a giant U-shaped valley that is the telltale signature that this was filled with ice, again, only 20,000 years ago. That was a big river of ice. So it's not the only place in the world where we have that kind of topography. This is Torres del Paine National Park in Chile. Again, the beautiful glacial terrain with huge U-shaped valleys that, again, only a short time ago were filled with ice. Elsewhere in North America, where I live in the Great Lakes area, the Great Lakes basins themselves were excavated by the glacial ice moving to the south. And a little bit further to the east, in upstate New York, this is the shore of Lake Ontario. And these stripes here, some of you will recognize, those are the Finger Lakes of upstate New York. And they, too, are glacial valleys carved by the ice. If they had actually extended to the sea, we would call them fjords. They're very much like fjords, long, narrow valleys carved by glacial ice. And, of course, those deep valleys that do go to the sea are what we call fjords. Here in Norway, you can see a seagoing liner coming up the fjord. Fjords are found in Scandinavia. They're found in the Alaskan Panhandle and Western Canada. They're found in southern Chile and in New Zealand. There's a special geography for the formation of fjords. I'm not going to go into that, except to say that I've often called fjords the gift of the ice ages, that it's a beautiful type of landscape that has resulted from the ice of the last ice age. So ice was big, abundant. It did all kinds of gorgeous work on Earth's landscape. And for the few people who were around at the time of the last ice age, they had to eke out a living. It wasn't very easy. They were certainly buffeted by the powers of nature. Most of the daily work was finding food. And so here are some of our early occupants of the continents working hard to make a go of it on that particular day, and showing already the very clever ingenuity that has made the human race such a prominent feature on the earth today. Now, leading up today, there's much less ice, as I mentioned. In the northern hemisphere, the ice that is left is largely on Greenland. Here's the island of Greenland. It has about a mile to a mile and a half of ice on it, covering most of the island. And the remaining ice that you see here, oops, sorry about that. I knew I'd make that mistake sooner or later. The remaining ice you see here is what we call sea ice. This is just simply the Arctic Ocean, the frozen seawater of the Arctic Ocean, and it's much, much thinner than the big pile of ice on Greenland, which, as I said, is over a mile thick in its thickest places. But all of Canada today, except for the northern islands, is free of ice. Europe is free of ice. Siberia is free of surface ice. It has frozen ground still below it in the form of permafrost. So there's much, much less ice today. But, as I said, there's a lot more people. Now, when the glaciers were melting, when the last ice age came to an end, there were perhaps 1 million people on Earth, and population grew slowly, but finally reached 1 billion in about the year 1800. But it only took another 130 years to reach 2 billion in 1930. And it only took another 45 years to reach 4 billion in 1975. And it will only take another 45 or so years to reach 8 billion, to double again in about 2020. So the Earth's population has grown dramatically, and you're seeing that result in this graph only since about the beginning of the 18th century. Here, 1 billion, there 2 billion, 4 billion, and getting up to 8 billion around 2020. So the Earth's population has grown dramatically in the last few centuries, And not only has the numbers grown, but also the capability of humans has grown dramatically as well. Humans today have become the most powerful agent of change on the face of the planet. And that's one of the important messages to take away tonight. Don't let anyone tell you that humans are not powerful enough to affect the climate. They're not powerful enough to do lots of things. We know that that's not true, and I'll show you some of the many, many ways that we know how powerful the human population is. Now, the first example I'll give is simply that humans have cut down a lot of the trees that existed in North America. When the Europeans first came to the USA in the time of the Pilgrims, the entire eastern part of the country was forested, and much of the Mountain West and Pacific Northwest was as well. But as the population grew, by the middle of the 19th century, there are large areas that had been deforested. And by 1920, you can see that nearly all of the original primeval forest in the eastern states was gone, including here in my home state of Michigan, where you go from a fully forested state in 1850 to an almost nude state in 1920. So humans have made a big impact on the land use, not only, of course, in North America, but in Europe and everywhere else where the population has grown. Now, this has an effect on the climate in several different ways. One, of course, is that trees, because they're green plants, consume carbon dioxide from the atmosphere. Carbon dioxide is a greenhouse gas, or a heat-trapping gas, if you like to think of it that way, or a blanket over the surface of the Earth. And trees tend to pull out carbon dioxide from the atmosphere as their nourishment. But if you cut them down, they don't do that anymore. And so when you deforest an area, you're removing one of the checks and balances of the greenhouse efficiency in the atmosphere that has been with us for a long, long time. It also changes the color of the surface of the Earth from a dark color, which absorbs solar heating, to a much lighter color of the soil, which reflects more of the solar heating. And so it's changing the balance of the heat that is retained by the surface of the Earth from the solar heat. Now, humans have also learned to excavate very effectively. Humans have built really huge machines that can dig and scrape and move earth. Today, humans move more earth than rivers do. And let me show you some of the examples. This is from sites in the Appalachians where entire mountaintops are being removed to expose coal beds that are fairly close to the surface, within 20 or 30 meters of the surface. The very process is called mountaintop removal. It has a tremendous amount of hubris to it to simply say, we'll remove the mountaintops to get at the coal. But this is going on in many, many places in the Appalachians. In the western area, this is in Utah, this is the Bingham Copper Pit. It's a hole in the ground that is approaching a mile deep. It's an astounding big hole if you've ever had the opportunity to peer over the edge of it in Utah. So we have become tremendous agents in changing the face of the earth through land use change and land removal. Now, we've also done tremendous things in taming the hydrological cycle. The hydrological cycle acts to evaporate water from the oceans. It gets transported by the atmosphere, and some of it drops onto the continents and eventually rolls off and flows back to the ocean. So that's why we call it a cycle. But humans have interfered with the runoff phase by building huge dams on the face of the earth. This is the Hoover Dam on the Colorado River. Now, in the USA, there is not a single river of any significance that is not dammed at least once and sometimes many times. Colorado River has 5 major hydroelectric dams. The Missouri River has 5. The Columbia has several. Every stream in America and most of the other high potential hydroelectric rivers around the world have been dammed. Another interruption of the hydrological cycle is shown here. This is the Aral Sea in Kazakhstan. Now, this is a satellite view, but what you're looking at is the Aral Sea towards the end of the 80s, and then again 20 years later, it's nearly dried up. Now, how has this happened? The drying up comes from the diversion of waters. The Soviet Union simply diverted water into the deserts of Kazakhstan to use for irrigation, and in the process dried up the Aral Sea. Now, how big is the Aral Sea? The Aral Sea was in the top 5 of lakes in the world. It was about the size of Lake Huron in the Great Lakes, and today it's reduced to, as you can see, almost nothing. Aral Sea used to be the home of a big Russian fishing fleet, and provided about 20% of all the fish consumed in the Soviet Union. And today the fishing boats are lying idly on the sand of the Aral Sea. Not only have we interfered with the hydrological cycle at the surface, we have also done the same with subsurface water. Subsurface water or groundwater is water stored below the surface of the earth in the pore spaces of the sediment and in fractures and in other types of rock. And we have been pumping that water out of the subsurface now for probably in earnest about 75 to 100 years. So much so in the Great Plains that with this very extensive form of pivot irrigation, the center of every circle is a deep well that's pumping water from the subsurface, that the water table has dropped several hundred feet, and in many places the subsurface reservoir is being depleted dramatically. We're taking water from the subsurface so fast there's no chance of replacement through normal processes. So effectively we're mining the water of the Great Plains. Prior to the use of irrigation, the natural boundary of irrigation in the Great Plains, or the natural boundary of normal precipitated agriculture, was the 100th meridian. To the east of that, there was enough rainfall for agriculture. To the west of that, you needed irrigation. So the entire Great Plains in the western Dakotas, Nebraska, Kansas, Oklahoma, Texas, is all producing agriculturally by mining the subsurface water. We have also left our signature on the oceans. This is a picture of the mouth of the Mississippi River coming down through Louisiana. Out here, this is the chemical pollution of the Mississippi outlet area that comes from the washing out of agricultural fertilizers from the vast interior of the Missouri and Ohio and Mississippi River drainage basins. And the fertilizer has so fertilized the oceans that microorganisms have used up all the oxygen, and the larger fauna can no longer have oxygen to live, and so these are called dead zones. This has been going on for the better part of our industrialized agriculture. Of course, recently we also have seen a new assault on the Gulf of Mexico. Here's the scene of the BP rig before its demise, and it's sinking to the bottom of the sea, and of course the pollution that we're seeing every day now on the television with no end clearly in sight is just yet another indicator of the way in which humans have left their mark on the planet. It's not just the land and the oceans, it's also the atmosphere. Here's a picture of one of our large cities. It could have been Los Angeles at one time. It could be any number of our cities that had atmospheres so polluted by smoke and exhaust from industrial processes. This, of course, in many places doesn't stay where it's produced. It gets transported, and the acid rain of the northeastern part of the USA and southern Canada came from the smokestacks of the coal-fired power plants in the Midwest that simply were, the exhausts were wafted to the east. The burning of high sulfur coal led to sulfuric acid as precipitation. It changed the pH of the lakes, and it killed many of the forests. And that was the consequence of our appetite for energy. We have also polluted the atmosphere in other ways, not even aware that we were polluting it. But the creation of the ozone hole over Antarctica was a result of the emissions of the chlorofluorocarbons into the atmosphere. The chlorofluorocarbons were a human synthesized chemical. They are not natural chemicals, and they were invented to replace other more dangerous chemicals that were used in refrigerants. So whereas your grandparents may have had an ammonia refrigerator, none of us grew up with ammonia refrigerators. And we have these modern refrigerators that have an inert and non-toxic refrigerant, namely the CFCs. But little did we realize that the continued use of this family of chemicals was not being balanced by destruction anywhere. They were simply accumulating in the atmosphere and eventually leading to the destruction of the ozone. And then finally, of course, the pollution that is most related to climate change is the growth of carbon dioxide in the atmosphere. This is a graph of carbon dioxide growth since 1957. It's measurements on the island of Mauna Loa in Hawaii, but you can measure carbon dioxide nearly anywhere you want, and you'll get the same result. And in 1957, the level was about 315 parts per million in the atmosphere, and it's been growing year by year, every year, with some lesser, some greater periods, but today it's up to about 390 parts per million, and it's increasing by 2 to 3 parts per million every year. Now, this is a 50-year window into the accumulation, but of course the accumulation of carbon dioxide from human activities, from the burning of the fossil fuels, began long before that. So you need to take a longer look at the carbon dioxide in the atmosphere to appreciate where this series of measurements fits in. So here we're on a much expanded time scale. We're now looking at 400,000 years over here on the left-hand side and up to the present day over there. Now, this is truly looking at it on a geological time scale. Hundreds of thousands of years going back. This kind of a record goes back almost to 1 million years. But what you see here is that there have been times where carbon dioxide fell and then increased and then fell and then increased, then fell and then increased, then fell and then increased. And those correspond to 4 ice ages, the most recent of which reached a maximum only 20,000 years ago, and then we began to warm up. But the important thing that the ice ages have told us is that accompanying the climate change as severe as an ice age meant an oscillation between about 300 parts per million and about 200 parts per million of carbon dioxide in the atmosphere. So that was the full range of natural variability in and out of ice ages. Now we look at the present day, and in the beginning of the Industrial Revolution, the carbon dioxide content in our atmosphere was 280 parts per million. When we started measuring it in earnest in 1957, it was already at 315. And today, at 390, we're here. We have moved entirely out of the range of natural variability of the climate process over the past 500,000 years. And at the rate at which carbon dioxide is continuing to grow in the atmosphere, we're here right here at 390, by the end of the century, if there are no changes, it'll be getting up towards 700 parts per million. This is, as I call it, the big inadvertent experiment with Earth's climate. No one anticipated when we began the Industrial Revolution that the product of combustion, of the use of energy, was going to change the climate. But as the number of people grew and our industrial cleverness grew and our energy consumption grew, it turns out that we moved beyond the range of natural variability in about 1950. And from then on, we've been on the big inadvertent experiment. Now, not long ago, when you may have heard the Large Hadron Collider in Switzerland, this massive atom smasher was put into operation, and there was a lot of news coverage of it. And some of the scientists said this was the largest experiment ever undertaken by humans. And I said, no, it's not. The largest experiment ever undertaken by humans is the one that we've undertaken inadvertently with the climate and our changing chemistry of the atmosphere. So I've gone through this long litany of changes that humans have brought to the face of the planet to persuade you that yes, indeed, humans are really capable of changing the planet. And so whenever you hear someone say, oh, I just can't believe that we're able to do this to the climate, you tell them we've left our signature in so many ways. Don't be surprised if we're also changing the climate. Now, what has this done in changing the climate? Well, the main thing is that it has led to a warming of the atmosphere. And here we're looking at a temperature record that extends from the end of the towards the end of the 19th century up to the present day. And you can see, of course, year by year, there's lots of ups and downs. There's warm years, there's cool years, there's warm decades, there's cool decades. But you don't need to be a rocket scientist to see the general trend is up. I didn't have to put that green line on there. I know that you're all clever enough to see that trend without my guiding you. And in particular, since about mid-20th century, right about here, the rate of change has gotten ever faster. And so you can see that where we are up here right now are the warmest decades in the entire instrumental record. Now, a particular piece of mischief that you'll often hear is that some of the climate skeptics say, what's all this talk about warming? The climate has been cooling for the last decade. Well, let me show you how specious that is. 1998 was a warm year, and these are cooler than that. And so they say, well, look at that. That's a downward trend. And no matter that these are the warmest decades in recorded instrumental record history, they call upon that as a cooling trend. Well, we can see that that's silliness. Now, if you don't like the man-made thermometers that go into this kind of a record, this comes from reading weather stations, thermometers around the globe, and from getting temperature measurements from the sea surface, from buoys and ships at sea. I point out that you don't have to have human thermometers to tell you that there's climate change. We have a lot of natural thermometers. Nature does have a number of thermometers, and much of the wildlife of the earth are natural thermometers. Flowers will bloom earlier when it gets warmer, and birds will lay their eggs earlier, and fish, I probably shouldn't say anything about fish here in an aquarium audience, but I'm sure it has effects at sea that change their their distribution, and probably their mating and spawning habits. The natural world just responds to the climate, and the fauna and flora find their preferred zone. And if they have to move, and if they can move fast enough, they'll relocate. And so we see species on the move today. But the most important natural thermometer, and it's the one that I emphasize in my book, is ice. And I like ice in part because it is a very sensitive thermometer. It's close to its melting point, and small changes in temperature mean big changes in the distribution of ice. But it's also a neutral thermometer. And this is the only quote you'll see from the book. But ice asks no questions, presents no arguments, it reads no newspapers, it listens to no debates. It's not burdened by ideology, carries no political baggage. It just changes, when it gets too warm, it just changes from solid to liquid. And that is nature's way of talking to us. When people talk to me and say, oh, I don't believe in climate change, it's all political, I say, there are no Republican floods or Democratic hurricanes. I said, that's nature talking to us. And if you can't hear nature talking to you, you're in trouble because nature is an unbiased witness to this. And it tells its own story quite separated from the political debates that we often hear. So let's have a look at ice. The ice is retreating around the globe today. The earliest places where it became apparent were in mountain glaciers around the world, in the Alps, in the Rocky Mountains, in the Andes, in Africa on Kilimanjaro and Mount Kenya, and in the Ruwenzori, and in Asia on the many glaciers on the Tibetan Plateau and in the Himalayas. And let's have a look at some of those. One of the best documented glaciers, just because there's lots of imagery of it, is the Rhone Glacier in Switzerland. And here's a picture dating from 1850. I think actually this is a postcard. And in 1850, the Rhone Glacier came from the uplands, traveled down this steep slope, had a big lobe of ice here in the valley. And that was the characteristic in 1850. But in 1927, it's still, of course, coming from above down the steep slope, but the big lobe is now gone. This is in 1927. In 1981, the valley above is still full, but the steep slope is now bare, and down below, of course, the lobe is gone. And I want to call to your attention this little zigzaggy road that is the tourist road into the area now. There's a little hotel sitting right up here, Hotel Belvedere. Just a couple years ago, the view from Hotel Belvedere looked like this. The upper valley is now empty. As I say, this is not just something peculiar to the Rhone Glacier or to the Alps, but it's true all over the globe. In Glacier Bay National Park in Alaska, this is a picture, I think it's the McBride Glacier, and it's a picture taken in 1988 showing the snout of the glacier. But in 1966, it was out here. This is a sedimentary deposit, a moraine of the glacier, which was laid down when the glacier extended out this far. And it's almost a kilometer of retreat since in the 22 years shown there. Way in the southern hemisphere, this is a picture in the Beagle Channel. This is a picture of one of the many glaciers. There's probably a dozen or 15 glaciers that are spilling off the South Patagonia ice field down to the Beagle Channel. And you can see this picture taken in the late 1990s shows that the big area of bare rock was covered by ice, and that ice is gone, and the upper level now is all that you see of it. But in 1835, when Charles Darwin was sailing through this channel, which was named for his ship of the time, HMS Beagle, he remarked about how all the glaciers were hanging over the escarpments and dropping icebergs into the sea, and there were navigational difficulties because of the great abundance of ice. So in the period since Darwin was there to today, there's been this retreat. And on Kilimanjaro in Africa, here are two pictures of Kilimanjaro, one in 1978 when there was a substantial amount of ice still at the top, and one in 2005 when there's almost none. And the graph that's superimposed on the picture over here is a century-long graph of ice distribution on Kilimanjaro in terms of area, and there's been a steady decline. This is the last measurement, and you can see the projection to zero is just within the present decade. So the famous snows of Kilimanjaro are almost a thing of the past. Now, it's not only the mountain glaciers, but the big ice on Earth, on Greenland and in the Antarctic, that's changing as well. Let's have a look at Greenland. Here are three views of Greenland over the last 20 years or so. The red areas show the areas affected by summertime melting. Now, every summer, some of the ice on Greenland will melt, usually the low-lying ice and the southernmost ice, the ice closest to sea level. And summertime will lead to some melting and some refreezing in the winter. And you can see the areas that were melting in 1992 were confined largely to the southern part and to low elevations. But in the later images, the red areas now go almost all the way around Greenland and are climbing to higher elevations. And in 2005, you can see that it's gone even higher up and are covering more and more area. So this increased melting of Greenland is ongoing, and what it has led to, which was totally unanticipated, is that what people thought the meltwater would do is simply flow off the ice and down to sea and add some new water to the oceans. But what they've now discovered is that it doesn't just flow off the ice down to the sea, but it burrows down through thick fissures, big cracks in Greenland, and plummets straight down through the ice sheet down to the base of the ice. And it's lubricating the base of the ice, and the entire ice sheet is slipping faster. And the glaciers all around Greenland that are fed by this upland ice sheet are accelerating. And so we are seeing ice slipping off of Greenland even faster than we had imagined only 2 decades ago. And the other ice in the Arctic, it's the Arctic sea ice, which I mentioned to you earlier. The big extent of white here is just frozen seawater in the Arctic Ocean. The Arctic Ocean, for most of human history, has been frozen, and even in the summertime, while there's some breakup and melting on its fringes, even in the summertime, most of the ocean remained frozen. But a few decades ago, that started to change. Before looking at those, let me show you what sea ice looks like close up. Here you can see some sea ice in the foreground. It looks like a very thin sheet. Actually, it's about 1 meter thick, which is still pretty thick ice, but nothing compared to the several thousand feet of ice on Greenland or Antarctica. And so this sea ice in the Arctic has been changing its summertime breakup. And here you can see the Arctic sea ice at 3 different times in 1980, 2005, and 2007. And this is September sea ice. September sea ice, that's the extent of the ice at the end of the summer. So it's the smallest area. It's undergone an entire summer of breakup and melting. And here you can see that in 2007, the darker blue on that, this extent of the remaining ice was about 40% reduced from what it was only 25 years prior to that. And what doesn't show on a map like this only shows changes in area, but there are also changes in thickness. And the average thickness of the Arctic sea ice has been reduced by 50%. So we have seen a dramatic change in the Arctic sea ice, and if this trend continues, we'll see an ice-free Arctic Ocean in the summertime, probably before mid-century. So the changes in the Arctic sea ice are a very big change. It will certainly open up a marine environment to exploitation. The fishery fleets of the world will certainly be eyeing that as a place where it's previously been untapped. And so it'll be of great interest. Of course, it's not only the biological resources, but the exploration for oil and gas will also be picked up with renewed vigor. So, as I say, big changes are coming to the Arctic Ocean. Now, at the other end of the globe, the Antarctic, this is a map of Antarctica that basically shows a little bit of geography. Along the Transantarctic Mountains, there's a natural dividing between what we call the East Antarctic and the West Antarctic. And the East Antarctic has a bigger pile of ice on it that flows outward to all directions and also across the Transantarctic Mountains into West Antarctica. And the spillage of ice off the Antarctic ice sheets often extends off into the sea, creating what are called ice shelves. This is not sea ice. This is very thick land ice that is flowing off via glaciers into the sea, and it makes a big floating table of ice. It's something like if you imagine a scoop of chocolate ice cream and you pour marshmallow sauce on it, and you put so much marshmallow sauce on it that it not only spills off, but it starts to fill up the saucer around it. Well, that's what these pale blue areas are, these big ice shelves of the Antarctic. And the ice shelves themselves are breaking up now, and some very well documented breakups here along the Antarctic Peninsula. This is the finger of land pointing up towards South America. And earlier in this decade, a big breakup of the Larsen ice shelf took place in a period of 5 weeks, and an area the size of the state of Rhode Island broke out from this earlier undisturbed status. And there's so much ice out into the Weddell Sea, the sea adjacent to that, that for a while navigation in the Antarctic was imperiled by all of the big ice that was delivered by the breakup of the ice shelf. On the other side of the peninsula, there's the Wilkins ice shelf, which is in the process of breaking up here, but that breakup actually culminated this year so that these pieces are now scattered and beginning to float out into the open sea. And this is not small ice. There's no scale on this, but let me show you a picture close up of a research vessel up against the edge of one of these ice shelves that is breaking up. This is big ice, and every time that you remove ice from the continent and put it into the ocean, it raises sea level. It's like dropping an ice cube into a beverage glass, and you don't have to wait for it to melt. The level goes up right away. So one of the consequences of seeing ice come off of Greenland and come off of the Antarctic is that sea level is rising, not just because of that ice, but also because the sea itself is warming, and warmer water is less dense than colder water, and therefore it occupies more volume. So we see sea level rising. Here in the 20th century, sea level rose about 20 centimeters, and the rate at which it's rising at the end of the 20th century is more than twice what it was at the beginning of the century, and it is continuing to accelerate. The predictions for sea level rise in the 21st century, current century, is somewhere between 1 and 2 meters of sea level rise. I don't have a preference, but either one is bad, and I'll show you some of the consequences of what a 1 meter rise in sea level would be. Here's a picture of the capital city of the Maldive Islands in the Indian Ocean. The Maldives have an interesting statistical record. They are the lowest lying nation in the world. There's no point in the Maldives that is more than 7 feet above sea level. You can't count tall buildings. But the base of the islands is nowhere more than 7 feet above sea level. And here is a nation of several million people where the government is actually trying to buy land in adjacent countries for the eventuality of having to move if sea level continues to rise. Now, you don't have to look to the Maldives or to the South Pacific or other distant places. A 1 meter sea level rise means a lot in the USA as well. Here's the Gulf Coast and Florida Peninsula, and the areas shown in red are the areas that would be inundated if sea level rose by 1 meter. This is about 3 feet. You know, from the floor up to your navel is a good measure of that distance. And much of the Everglades would be lost. All of the barrier beaches on Florida would be lost. Much of the Mississippi Delta and southern Louisiana would be lost. And if the Gulf Coast seems remote, although I know it's not remote now because it's in the news every night, but in California, here's a picture of San Francisco Bay. Here's San Francisco right here, the Golden Gate, Oakland across the bay, and then up the river towards Sacramento. The red areas here likewise show you what 1 meter of sea level rise would mean. And all the white on these are populated, built-up areas, and so you can see the impact of 1 meter sea level rise. And Long Beach itself, of course, is not immune to a 1 meter sea level rise, although I didn't bring a map of that for the local area. Now, that's the immediate future. What if we lost some big ice, say from Greenland or West Antarctica? Greenland, you can see, and West Antarctica are about the same size, and they have enough ice on them so that if you would lose the ice entirely from Greenland or entirely from West Antarctica, sea level would rise about 6 or 7 meters, around 20 feet. And if you lost it from both, it would be about 40 feet of sea level rise. And the big pile on East Antarctica has, of course, the biggest amount of ice, and if we would lose all of that ice, of course, all the rest of the ice would have gone earlier. Sea level would be about 250 feet higher than it is today. No one even needs to imagine what catastrophe that would be. But the issue of Greenland losing its ice in the coming centuries, or the West Antarctic, or combinations of both, are both within the realm of feasibility, of possibility, if in fact we don't have something that will mitigate the climate change that's underway. If we in fact did lose enough ice to lead to a 6 meter rise in sea level, here is the Gulf Coast area now with 6 meters. You can see nearly all of southern Florida is gone, and the inundation towards the center of the peninsula is much more severe. And then for the Bay Area, it continues to grow. So the biggest casualty, of course, of rising sea levels is that it creates climate refugees. It creates people who have to move. If sea level comes and occupies your home, you pack up if you can and go. In the olden days, before the Earth was highly populated, and when we had so many fewer people, and there was plenty of ground to move to. But today, if you lose your home near the seashore and you want to move inland, you discover someone else is living there already, and they're not keen to have you moving in. So there's a tremendous amount of social disruption that will accompany a rise of sea level, as well as the damage to infrastructure and harbor facilities, which have in great abundance here in Long Beach. And so when you think of the population displacement alone as a function of rising sea level, it's a graph shown here with sea level rise on the horizontal axis, 1 meter, 2 meters, 3 meters, and then population displaced by sea level rise. A rise of 1 meter displaces 100 million people worldwide. And a loss of 6 meters, or a rise of 6 meters, is close to 400 million people worldwide. The population of the USA is only about 300 million. And so you can see what we're talking about in terms of large-scale population displacement. Well, let me review just quickly the timetable for these various consequences of losing ice. On the short time scale, that's the next few decades, we're going to see the loss of tropical and temperate mountain glaciers and an ice-free Arctic Ocean. I already mentioned some of the consequences of an ice-free Arctic Ocean, but losing the tropical and mid-latitude glaciers has severe impacts on the agricultural water and the municipal water and domestic water supply for about a third of Earth's population. So that too will be a tremendous social disruption if in fact the mountain glaciers disappear. For this century, which I still call a short timetable, we'll be seeing a sea level rise of 1 to 2 meters. On the longer time scale, meaning in the next several centuries, we might begin to lose the ice from Greenland and West Antarctica, and each of those would produce 6 to 7 meters change in sea level. And then we'll begin to see other consequences of melting of the permafrost surrounding the Arctic, and that has an interesting consequence that there's a lot of methane, another greenhouse gas, that's locked up in the permafrost. And if we begin to melt the permafrost, or defrost it, so to speak, we'll release that, which simply adds to the greenhouse gas load in the atmosphere and accelerates the warming even faster. And so then finally, something that will let you breathe easy, the loss of East Antarctica, the big pile of ice remaining, is not likely to come quickly because there's so much ice and it's so climatologically isolated that there's little in the way of calculations that suggest that we'll face that in anything less than a millennium. So those are pretty grim consequences. And the closing slide that I want to show is the Chinese word for crisis. The Chinese word for crisis is actually two words, two symbols. One is danger, and one is opportunity. It probably opens an interesting philosophical window into the Chinese mind. But it is a good word, a good term for our current situation, that the crisis over climate change is, in fact, one of danger, and much less spoken about is one of opportunity. The danger I've described to you, we're going to disrupt agricultural water, we're going to see rising sea levels, we're going to see human displacements, we're going to see all kinds of things if we don't get climate change under control and reduce it eventually to its pre-industrialized excursion. But what are the opportunities? You know, what am I talking about here when I talk about opportunity? Well, the opportunity that comes is that this gives us a chance to rethink our modern industrial economy. It's a chance to stand back and say, the fossil fuels have been great. They've done a lot for us. They've certainly enhanced our standard of living. But we didn't know it. We were conducting this big inadvertent experiment with our climate. And now we're seeing the results of that experiment. And so we're going to find a new way to do things. And the new way will be to reinvent the source of energy that we use to fuel our modern industrial economy. We're going to find ways to use the wind and the sunshine and the biomass and nuclear energy, other non-carbon sources of energy. And the opportunity comes for the nation or the population that is fastest out of the starting gate in these new technologies and does the research and creates the breakthroughs that will make alternative energy economic and widespread. That is an opportunity to bring great prosperity, wealth, jobs, all the things that we think of as the benefits of a modern industrial economy, that those can accrue to the nation or nations that's successful in breaking away with leadership in those fields. And the question is, which countries will those be? Currently, in wind technology, 9 jobs out of 10 in the wind industry are not in the USA. They're in China, they're in Europe. And that's indicative of the dragging of feet that's taking place in the USA about an energy policy, a transformation of the way that we do our industry, the way we power our industry. And if we dilly-dally too long, the train is going to leave the station, and we're going to be standing there wondering what has happened. So it's an opportunity, but the window of opportunity is not going to be open forever. I like to end with a perspective offered by Winston Churchill, who described a pessimist as someone who sees the difficulty in every opportunity. But an optimist is someone who sees the opportunity in every difficulty. And that's the situation we're in today. We're in difficult times, but we all need to be Churchillian optimists and see the opportunities that are being presented to us to remake our modern industrial economy and stride out confidently in the 21st century, remaking the way in which people on Earth live with their environment without sacrificing in any substantial way the quality of our living. So I want to urge everyone to leave tonight being a Churchillian optimist and realize that this is not all a tale of gloom and doom. There are dangers, but there are also opportunities, and we need to seize the opportunity. Thank you very much. Good. We need a lot of engineers.
On the historical geologic timescale, where ice ages and stuff, what is the forcing mechanism that brought it back down, brought the temperature back down?
But the oscillation, it relates to the orbit of the Earth around the sun and the orientation of the Earth within that orbit. Now, the orbit of the Earth is elliptical, but the ellipse changes. It becomes more cigar-like and then more circular and more cigar-like and more circular. And so that has an effect on the seasonal contrasts, and that has a period of about 100,000 years. And that seems to be the pacemaker that gives this 100,000-year oscillation in the climate that showed up in that graph. The other factors that play a role in it are the tilt of the Earth's axis, which today is 23.5 degrees away from the perpendicular to the plane of the orbit. But that oscillates between 21 degrees and 24 degrees. We're currently at 23.5. Greater inclination also creates greater seasonality. Then there's a third factor, which is the way in which the rotation axis is pointing at the time of the closest approach to the sun, whether it's pointing away from the sun or towards it, and that determines which hemisphere gets the benefit of the intense summer. So those three things beating against each other seem to be what's controlling the coming and going of ice ages in the last 3 million years. But they are pacemakers. They are not the whole story, because the amount of sunshine variation it doesn't seem to be enough to do the entire job. So there have to be feedback mechanisms that get triggered by these pacemakers. Long answer, but I know an engineer can appreciate that.
Henry, maybe I'll ask one. This afternoon we talked about whether the situation in the Gulf, whether it's an opportunity. And Tom Friedman's op-ed piece in last Sunday's New York Times, it ends with the statement that the situation in the Gulf is a disaster, and a disaster is a terrible thing to waste. Could we use that disaster to help move us in the direction of renewable energy?
Jerry and I were talking about this earlier today, and I have said that a slow-moving disaster doesn't do the job. Climate change is a slow-moving disaster. But you need something that is like a whack over the head with a 2x4 to get your attention. And I gave the example that at the beginning of World War II, the attack on Pearl Harbor was a 2x4 that got America's attention. And it led to immediate reindustrialization of the country. All domestic manufacturing ended. No more refrigerators, no more washing machines, no more passenger autos. Every factory in America started building tanks and airplanes and cargo ships and jeeps and the like. And in only a year, there were more airplanes manufactured in one factory in Michigan than in all of Japan. It shows you what a change of great scope took place in America in 1 year to rally against the threat. Now, I often ponder what could make us rally against climate change, which isn't a 2x4. But along comes the Gulf spill. And that's captured America's attention. Let me tell you, I wouldn't think that watching a live video cam of an oil well spouting at the bottom of the ocean would attract so many visitors, so many viewers, but people are fascinated by that and disgusted by it and alarmed by it and distressed by it. And it is having the effect of getting our attention. And what it draws attention to is that we have a tremendous dependence on the fossil fuels. And this dependence has given us insecurities in our foreign policy. It has made us the world's largest debtor nation, where we export almost $1 billion a day to feed our fossil fuel addiction. And it is also causing climate change. And so a friend of mine has said that, energy insecurity and our status as the world's largest debtor nation and climate change are not three separate problems. Those are three facets of the same problem, a misguided national energy policy. And if we can move off the fossil fuel dime and onto a pathway of renewable, sustainable energy, we will address all three problems simultaneously. And so, but it takes something to move us off the dime. And that's what I think Tom Friedman was right and Jerry's right, that never waste a catastrophe. It's a teachable moment, as we say in the classroom. And this may capture the attention of America in ways that no amount of my talking about melting ice ever would. This is something that is much more palpable and much more visible to large numbers of people.
If that is true, why didn't we learn anything from Katrina? We went right back and are rebuilding New Orleans just the way it was before.
I think that the lesson from Katrina was not viewed as being directly linked to our energy consumption. Many people felt Katrina was an unfortunate natural disaster that, took down New Orleans, and it was part of our human folly to think that we could live below sea level with a ring of dikes and levees. But no one, or not many, associated that with an energy policy. And so this oil spill in the Gulf is different from Katrina in that it's directly linked to our energy appetite. Whereas I think Katrina, that connection wasn't made so clearly.
Okay, this is a hydrological and ice question. When the water falls through the moraines and into the base of the glaciers, and would be especially true in valley glaciers, alpine glaciers, but it would be true on anything. It doesn't just lubricate the glacier. If you've ever watched a frozen glass of ice thaw, the ice in the glass floats as soon as there's just a little film of water around the glass. It takes very little water to float the ice when the ice fills the container. So that water isn't only acting like oil down there or grease, it's lifting the glacier. And, if the water's halfway up on the valley floor, then you're lifting half the weight of the glacier because it's about the same, right? So I predict that glaciers may move a whole lot faster than people are ready for.
Well,
I guess that's being taken into account, and I've never met anybody that has.
The phenomenon of the acceleration of glaciers off of Greenland and West Antarctica has only been noticed, observed, and begun to be measured in the last decade. And so the real mechanisms by what's leading to it, the lubrication idea was a quick and easy one, but it may well be that there are buoyancy effects like you're describing, but the acceleration, for whatever reasons, is real and continuing to grow. And so that, in the last Intergovernmental Panel on Climate Change report, when projecting sea level rise at decades long through this century, all of the IPCC estimates were pretty much on the low side. Even the upper range of the estimates was less than a meter. But they had a big caveat in a big bold box in the report that said, this doesn't take into account any of the lubrication or other effects that are changing the ice dynamics. All that went into our calculation was warming of seawater and new meltwater coming to the sea. So the idea that we're sending new ice to the sea, not waiting for it to melt, never entered into the calculations because it was such a new observable. And that has only continued to accelerate. And so when I said that I think there's on the order of 1 to 2 meters of sea level rise for the 21st century, the IPCC report was short of 1 meter. But they acknowledged that it had to be a lower estimate. Couldn't be the total story.
Henry, it's a great book, and we want you to get busy on the next one so we can get you back here sooner than this last time.
I look forward to that. Thank you.
How about a big round of applause?
Yeah. Thank you.